first of all,
Patrick, you might want to check your sound. Apparently, the other people can hear us just fine. At least this morning, it was all right. Sound okay?
Good.
Good. All fine.
Let us begin. We have a webinar taking part in three different parts. First of all, an introduction about Scilab. Afterwards, a few demos from my colleague Paul, and use cases afterwards of industrial use of Scilab. Let us start with a few words about the story of Scilab. Scilab has been around for a few decades. The first version was released, actually in the early 80s. It wasn't called Scilab at the time, and it was basically just inspired by a free version of MATLAB and developed for about 10 years in the research institute called INRIA in France, which stands for Research in Informatics and Automation. They saw quite early that there was an interest from the community in this kind of software for numerical analysis and design of control system. So in 1994, the first version of Scilab was released with an open source license and distributed freely over the web, on the FTP first of all, and afterwards on Scilab.org. It's only in 2003 that with a consortium formed from different industrial companies that the researchers were figuring that there could be an interest also from the industry. So they gathered with companies such as PSA, Peugeot, Renault, Airbus, the French Space Agency, also process industries such as ArcelorMittal, and together they try to make Scilab as a industrial software. At the time, they realized that these companies had some difficulties to implement in industrial environments. So that was the reason, together with the Scilab consortium in 2010, of the creation of Scilab Enterprise. And in 2012, as the purpose of this consortium was fulfilled, Scilab was good and stable software. Came to Scilab Enterprise. So today, here at Scilab, we are the small development team, pushing Scilab further. And as of today, on this slide, there's quite an interest, big interest on the software from our community website, Scilab.org. You can download it, and there's around 100,000 downloads per month of this software worldwide. It's first of all, from France, it's the biggest source of downloads, but also from America, a lot of downloads in South America, such as Brazil, but also in US, in India, where there's a lot of educational use of Scilab. And they are training, several thousand engineers with Scilab every year, and also in Japan, in India, in China. So when you download Scilab, this is again, I said, the distribution, the open source distribution of Scilab. It is composed of three parts. First, numerical analysis engine itself, and the second module would be an alternative to Simulink. It's called XCOS, It is for the modeling and simulation of dynamic systems in both continuous and discrete time domains. This is not the focus here, but well, if you have questions afterwards, we can also discuss about these topics. And the third part is a server-side software called Atoms. You have a public repository at atoms.scilab.org, where you can download additional toolboxes. There's around 200 toolboxes from us and from the community. And you can also contribute your toolboxes, your code in this form on Scilab, on atoms.scilab.org. And basically, it's also with Atoms also enabling to download and install directly from the environment of Scilab these toolboxes in quite easy manner. So this is just an overview of what the distribution is offering. And today, our subject of test measurement and signal acquisition. Here you've got a few examples of what we've been doing in the past, especially with the Nasser instrument, which is quite a good partner in the field. Today we'll be talking a bit more about Scilab gateway inside LabVIEW, but notice that there are some other capabilities around Scilab in order to make signal acquisition and instrument control. Just a small introduction about the Visa toolbox, which is also another module that you can add up to Scilab directly in order to acquire your signal and control instrument directly from Scilab this time. So this is a toolbox which is based on the standard Visa, and Visa stands for Virtual Instrument Software Architecture. And well, it's actually supported by a lot of measurement device manufacturers. So if you have a national instrument device for an oscilloscope or signal generation, you can basically control it from this toolbox. And also on this topic, what we released yesterday on the social networks is a few examples of how you can use Arduino. So Arduino is basically just a small board. It's really low cost. You can get it for 20 euros. It's also quite good to make signal acquisition. So if you go on our website, you get the live news of yesterday about a few tutorials about how to use Arduino as a acquisition board. And in this example here on the right, you've got also a tutorial on how to make this example of temperature acquisition. So this was it about the subject of signal acquisition and instrument control. We'll go a bit more in detail afterwards with Paul and demos. But just now a few words about, as I mentioned, our business model. I won't be too long about it. As I mentioned, it's basically services. What we propose at the moment is training, support, and development around Scilab. And soon we'll be also deploying a new offer based on cloud services. Well, basically, as a teasing, the first product that we'll be releasing is a platform for deployment of web application, of scientific web application. So basically what you can develop today within Scilab with algorithm and dedicated graphical user interface, you will be able to deploy it and make it accessible for your user directly through their browser. So yeah, also after the presentation, if you have questions. And some references just for you to understand in which environment used. As I mentioned, from the consortium, there are still quite a lot of CNES countries, France and Germany, also with Airbus, a bit in automotive, metallurgy and energy, and chemical and pharmaceutical are some process industries where there's also some uses of Scilab. We won't be going in all of the details of concrete use cases and an example of how industrial companies use Scilab. Just also for this specific subjects, ST, microelectronic, microchip, Xilinx, and some other hardware manufacturer also are leveraging the capabilities of Scilab for test and measurement, and they are interfacing their hardware with Scilab. So yeah, this was based on this introduction. Now I will let my colleague Paul tell you more about the SCILAB-LabVIEW Gateway.
Thank you. So I'm gonna take over on the desktop. So you're gonna start seeing my whole. Okay, you should be seeing my screen now. Welcome to the new people who just came in. As a reminder, please use the. Please use the button on the bottom right of the screen saying "Fit to Screen." So you might see better if my screen is too large or too small or whatever.
Yeah, and you can switch between the two views on this WebEKO platform. If it's here about some scripting, maybe you want to zoom in to the area where Paul has his mouse.
Right. So how does I've provided the two links for the one for the gateway and one for Scilab. So how does the gateway work? So you install it on your system, and it will add inside LabVIEW. So you need LabVIEW, of course. It will add a little frame that you can drag and drop to your diagram. LabVIEW has a MATLAB frame already built in, so that's present when you install LabVIEW, but the gateway has added the Scilab frame. So what you can do is drag and drop that frame around inside your diagram, which is what I did for this demo. When you install the gateway, you have 4 or 5, maybe a bit more. You have these demos already present, so you can load them from the VIs inside your LabVIEW directory. So you can find the demos that I'm showing today. I tweaked them a little bit for this session because the gateway was published 4 years ago in 2012. So it's a little bit different now. But still, it's basically mostly the same. So how I'm going to go on this demo. So you can see on my phone device that what I'm going to do is basically call an instance of Scilab as a process on my system. Yes. And I'm going to run some script inside it. So in this demonstration, I don't have a loop. It's only a one-shot. And what I'm doing inside it is I'm going to get some information about my system and my version of Scilab. So mind you that the gateway links to the last Scilab that you installed on your system. For me, it was Scilab 552, which is the latest long-term support version of Scilab. So when I'm going to run my demo, it's going to say 552 because it's the last one on my system. You can also see that I'm invoking some graphical capabilities in Scilab due to the plots 3D, which is going to summon a graphical plot. So let's. Regarding the inputs and outputs, what you can simply do is right-clicking inside your frame, and this in French means adding an input or adding an output. So it's going to be translated when you install it. So what I did here was to add 3 outputs. You can see that they're purple, so they are expected to be matrices of string or scalars or vectors. And I'm going to link them to LabVIEW indicators, which are the ones on my front device. So when I run my demo, it's going to run just once. And I'm going to see it's taking some time because it's invoking the graphical demo. So there you go. This is what you get when you just type plot 3D inside Scilab. And on my front device, I can see that I'm indeed Scilab 552, which is that was the VER, which was the result of get version. So in Scilab, when you type get version, you get Scilab 552. You get your version of Scilab. The rest is the result of get debug info, which is helpful to us sometimes to zoom in on a problem. If you guys have problems, crashes with your Scilab, it helps us knowing which is your configuration, which version of Scilab you're running, etc. And so this is a simple example of how the gateway works. So I don't need this anymore. So you see that I had 3 outputs, which I took and displayed them inside LabVIEW. It's going to be a little bit more complicated, but still very basic. So I have a graphical output inside LabVIEW. So this time I'm using LabVIEW's graphical features. And there is my Scilab script. And this is a little bit different from the demo that you will have available when you download the gateway, because it has been tweaked a little bit by me. To do it in a vectorized way and in a sequential way. So what I'm doing is, so what are my inputs and my outputs? At first, I have a few constants determined, and I inject inside my script. These buttons there, the max there, and the speeds there that I will tweak during the demo. And okay, when I run my script, I start by creating 2 vectors, which are going to be my x and y axis, and I'm going to compute the altitudes of my points, which is going to be represented by z. So in the vectorized way, you see that you create vectors. So x and y being vectors, you and you add them together, your output results. So you see that on the left, those are the inputs, and x, y, z, there are the 3 axes that I'm fetching from the result of my Scilab computation and transmitting them to the LabVIEW graphic. So running it, it looks like it's very slow, and it's displaying, it's like lagging. It's displaying like 1 image every 0.5 seconds. Actually, on my screen, it's very fluid. No problems. Everything happens immediately. So when I tweak the speed and on X and Y, I'm getting, for instance, if I put a small speed on Y, on X and no speed in Y, this is what I get. And I can tweak the magnitudes as well to get higher waves according to the X axis, or very low on the Y axis. This is very too fast. And so if I use the speed, you should be seeing a little more, this is more followable to the eye.
Yeah, it is just due to the internet connection. I think you don't see on your screen the right speed of displaying on our screen, but it's just due to the net connection.
It's due to lagging on my computer. You can try it because the demonstration should be on your system when you install the gateway. So you can try it and see that it runs really smooth. Even in the sequential way of doing the computations, it's really smooth because it's not done on so many elements. So it's still very fast. No, I'm going to continue. Okay, so the computation itself, the sequential way is much slower because Scilab is an interpreted language. So every time you use a for or a while loop, something that's sequential, you are connecting the compiled code that Scilab is a layer of. So Scilab is basically just a layer of an interpreter connected to some C or C++ or Fortran code. So every time you use for loop, you are you are communicating with this lower layer and back and forth as many times as you have iterations. So if you do the vectorized way, everything is much faster because you are reducing the number of communications that you're doing between your Scilab layer and compiled code layer. That's why the sequential code is much slower, and you can benefit from the vectorized way of coding in Scilab, which is pretty much a good benefit in LabVIEW.
There's also another question from Austin, who's it's not available in the 64-bit LabVIEW.
It is available. On this version of the demo, I used LabVIEW graphic, but on the previous demonstration, you saw that I could summon a 3D graph from. I'm going to open it again.
So yeah, to answer the question is 3D graphics from Scilab are available in both 32 and 64-bit version.
Right, look here.
Yeah, it's just a demo from the first.
This was the first demonstration called Scilab version, and it was inside my diagram on this demo. So, yeah. I have a plot 3D here, instruction, and that summons a graphical window from Scilab that was generated by Scilab.
So yeah, but we can also discuss this after the demos, if it's all right.
Okay. All right, for this demonstration, moving on to the next one.
Question.
Yeah. Well, okay, this is a very common signal processing example, which is amplitude modulation of a message. So I have my inputs are going to be a carrier signal, a modulated signal. The two first signals, which are carrier and message, are going to be generated by Scilab and transmitted to LabVIEW, built based on the three indicators that you see there. So amplitude, frequency, and phase that are going to be transmitted to Scilab and back to LabVIEW as signals, as vectors. So on the diagram, you can see that the carrier signal parameters are the three that I was mentioning, and the message that I was mentioning are going to be built by Scilab. So in Scilab, my inputs are scalars, simple scalars, which I'm gonna build vectors from. So here T is a vector because semicolon is the series constructor in Scilab. So T is a vector. Now I'm going to build my carrier signal based on the the scalar parameters. So FC is a scalar, T is my vector. This is a constant as well, a scalar constant. So this whole thing is going to be a vector. AC is also a scalar, so cos of a vector is a vector. So carrier is a vector. Same thing for a message. Basically, T is my only vector here. So those two are vectors. Now to compute the modulation signal, U is a scalar here. Message is my vector, and carrier is my vector carrier signal. So here we use the dot star operator that lets you compute the message and carrier are going to be multiplied just by element in an element-wise fashion. So AM is also going to be a vector, which is going to be, so you can see as output, carrier, message, and amplitude modulated signal. So running the demo. So it's running. It's welcome, sir. Running the demo, I can now tweak my my parameters. So I can say augment the frequency of my carrier signal, amplitude, and I want to put a small amplitude on my carrier, high amplitude on my message, so it sticks out, and rather low frequency. And you can see that the AM signal is reacting to this, because this whole thing is put inside a loop here, inside my diagram, which runs every shortest possible at a very high rate. And so at every rate, I'm transmitting my parameters, my new parameters, to the Scilab script, which computes the three signals and displays them on my front device. So this is the kind of thing that you can do, which is very common and very useful on the signal processing. You can also dephase your message or your carrier, which is see it as much because it's very small here,
which is quite typical in signal processing. There are some capabilities directly within Scilab to simulate signal, such signal, and make the same kind of operations on the signal. Here, however, it's interesting to link it with LabVIEW to make it in real time. Here, you could do it, linking it not just to this simulated signal, but also to link it to your hardware. And this would be also afterwards the next demo. It would be linking it to hardware, which is basically what you might want to do when measurement, when you want to link it to the hardware at some point. But just notice for here, as an example of this script, this is something that you could be running directly within Scilab in the simulation before implementing it in real time. Another thing is one of the advantage of using Scilab here as a script directly within LabVIEW is, for example, with the scripting language, you get the ability to define your own functions, your own mathematical operations, and this is something which is a bit more flexible than what you have here with LabVIEW native. Element-wise,
where have you been looking? Have you been looking on help.scilab.org? Because there is a page on this for every operator in Scilab. So there is a page. I'm not sure of which keyword you'd have to type to find it, but there is a page.
Maybe do search on Google element-wise operation Scilab help, and you probably will find it. Otherwise, you can also directly find the help within Scilab with command help if you have Scilab installed, obviously.
But
okay. We will go on with the fourth and last demo, and afterwards, if it's all right, Patrick, we will go on with this subject.
Patrick, when Jan takes over, I'm going to do a small research. I can find it. I don't remember the name right now, but I will find it.
Yeah, we can paste it in the chat so that
you
find it. And for the fourth demo here, we're actually going to cover a subject which has been also raised by Hannibal, is hardware connection, because obviously one of the big advantages of LabVIEW is to enable a wide range of hardware connection and capabilities. Here you've got a pretty basic hardware. It's showing it upside down, and what it is, it's acquisition board, really simple with connection with a PC, and here you've got also some volt input, and what we'll be using is basically just a simple sensor here, a microphone, but basically if you want to make some temperature measurement and some soft real-time hardware in the loop with a fan, for example, you can see some demos to do that. Here.
Alejandro, your question, you don't have to run, you just need to install Scilab on your system, and when you run your VI, it's gonna the framed Scilab script is gonna launch an instance of Scilab as a process on your system. So you don't need to. I have not launched Scilab. It's automated as long as Scilab is installed on my system.
Yeah, but here, so we're running on a PC. Also, to answer the question of Hannibal on his platform is Compact Trio. Well, basically, here it's a desktop version of LabVIEW and in Scilab. Well, if you're using maybe an embedded version of LabVIEW for your Compact Trio, we might need to look into it. It might not be so simple to just run your Scilab script on it. Otherwise, I mean, Scilab is compiled on different both architecture. I think there are some compilation on ARM processors, and it's distributed on Linux, on several Linux distributions. So you might find a way to have your Scilab running on your Compact Trio. But this is a bit more, well, let's cover it afterwards if it's all right. Let's go further with this first demo, I propose.
Okay, so this demo is larger than the other ones, as you can see. So this is getting more interesting. Diagram. I'm stating the sampling rate as a constant, and one that's going to pilot the NIDAC, and it's going to transmit the signal that it captures to. So first, it's going to the least interesting one is it's just going to output it on the same device. So this doesn't have a lot of interest, but it's also after a gain transmitted to a waveform graph, which is the graph that you see on your phone device. So as a raw signal. And it's translated as well to the tone extractor of LabVIEW. So this is going to give me my NI frequency here that's been captured by Scilab. So basically, it's just doing an FFT as we're going to do in our script. And so it's translated to the automated tool of LabVIEW for tone extraction, and it's transmitted to the Scilab script. So here, the tick command is going to start a timer to compute how long, just to to clock how long it has taken us to do all the computations, how long our script took. So the tick here is starting the timer, and the talk at the end is just outputting the timer at the time it's been called. So this is going to tell us how long our script took. So based on our sampling rate, we create our x axis. We are going to do an FFT on the signal that we caught from the microphone. And based on this FFT, which we are going to extract the highest frequency, so the peak of our signal. And we are going to compare this peak to a tone chart that's been saved on my system elsewhere. So here it's interesting to see that you can use the CSV read capabilities of Scilab. So here I'm opening so I'm opening as a standalone script, opening a CSV file, reading what's in nodes, is integer frequency. So that's why, as an output, I'm going to get integer frequency. It's because I've only mapped exact values. So this is what it's doing here. A min of an apt, it's going to give me integer value. So when I have a dominant tone, I'm going to output, so the amplitude, the fundamental frequency that I caught. So you can see that the orange outputs are the either double bits or real values, which can be scalars, vectors, or matrices. In this case, some are, yes, this is a scalar, this is a scalar as well. So no vector here. And one string value that's going to correspond to my the closest node match, for which I have found a match. And I'm going to output the size of my sample, just to show you that there is no trick here. I still have my sampling rate at the end of the simulation. So running it will show me at first nothing, and I have recorded on my phone an A node of 400 hertz. So you're going to see now that, so on the demo you see that there's a flat signal because there is no gain. So now I've pressed, you should be hearing the phone signal. And once I augment my gain, you can see that the bars are turning. NI is getting me an exact approximated frequency. I mean, it's not an integer value, but Scilab is outputting me, like I said, integer values because it's the closest one it's related to. As I speak, it's jumbling the signal. So, but basically, which is 0.024 for the whole thing, and the size of my sample.
It's in seconds.
It's in seconds, yes. Right. And the size of my sample, which is still the same.
Vignesh had a question also about this time to process and how real time it is. I mean, basically it's pretty much soft real time here because we don't have a real time operating system on our PC. It's just a simple Windows. But on this question, I suggest we can address it also afterwards in the Q&A. Yeah, I mean.
All right, I'm good. I'm good with the demos. Unless there are any questions about the demos, we can move on to the industrial use cases.
Yeah, let's move on. And here, well, you had some basics walkthrough on how to implement Scilab within LabVIEW. What I propose is we go on with after these 3-4 demos to some industrial use cases of Scilab in the test of and measurement. First of all, in the automotive field, here I've got an example of Peugeot doing some post-processing on test campaigns. What they do is basically acquire aeroacoustic data from here, this area, this rear mirror, and they are displaying it in the frequency domain, and afterwards also displaying plots of the concentration in dB of these frequencies on the mirror. For a bit more advanced use, here we've got a use case of the aeronautics industry of Dassault Aviation, and what they do is well, basically they export all of the data both from for data experiments. They are basically trying to find out what are the influences of the different inputs of the system to the output. And here you see some graphs. For example, here is a self-organizing map, and here some correlation between inputs and outputs. And also, what is interesting to notice in this typical field and in typical use cases, the use of kriging methods, is advanced statistical methods with the help of a module called DACE available on Atoms, and also the use of advanced optimization methods. Here it's a generic algorithm with the algorithm NSDA2. It's a multi-objective optimization, and it's directly available within Scilab, so you can check it out. Here, another example in the field of medicine and of the medical field from INRIA, the research institute, and they were carrying on a study on electrocardiography and basically trying to analyze the signal directly coming from the heart, from the activity of the heart in acquisition and in pre-processing, and afterwards trying to match some pattern of the signal. And moving on with another example here in the field of agriculture. In fields of Bavaria, they are attaching the hoop for what is making the beer, and to attach this with wires, they basically they design a machine which is monitored by Let's just finish this use cases, and afterwards we go in Q&As if it's all right. So here, as you can see, they are leveraging the Scilab gateway within LabVIEW for the diagnostic tool of performance analysis. Another example here, directly with the connection of measurement of highly precise measurement technologies of Dantec Dynamics in Germany, and they are displaying the deformation, vibration on material. so making signal processing of their signal and images within Scilab. Another example here in field of aerospace is basically going further in the writing code and making some hardware in the loop directly from a model that they developed within XCOS of air vehicle simulator. So here's the aerospace German Aerospace Center is it's modeling the helicopter and the behavior of an ACE-320 an airplane within this simulator, thanks to XCOS, and it's making this simulation in real time with this code generation and deployment on the platform. And the last example also here about hardware in the loop is directly from a pretty basic example of electrical drive. Here you got a motor, an asynchronous machine loaded with sensors, and basically with the help of Xilinx FPGA hardware, they are gathering back the data here through UDP connection directly on net back to the PC in order to display the phases of the current, of the intensity of the current and the tension within the motor. So this was it about all of these different use cases. Well, if you have now a bit more question on Scilab, and especially in this field of test node measurement, we are here to answer your question.
So anticipating on the further future developments of the gateway. As I said, the gateway was published 4 years ago, so we are testing a bit their interest in the community. That's what we're doing webinars, is to drum up interest on the gateway, and as if the community senses utility of it, we just need your feedback for the proceedings on the developments. So we might make it, I don't know, available for other software or some platforms, or if you maybe fix bugs, of course, or add documentation, whatever it's gonna put on the. Okay. So this is a test of the interest of this tool for the community.
So here I can see, yeah, some question also from Vignesh and from I think it was Pedro who said, yeah, I want to interface directly my hardware within XCOS or Scilab. And as I mentioned earlier, also we developed this module, the Visa toolbox for data acquisition and instrument control directly from Scilab. And well, since there's a possibility to create blocks and functions with XCOS to interface, get back.
You can, of course, you can have inputs and outputs in it, and you have a frame that calls Scilab instructions. So if you already have your code using the Visa toolbox, you can input it as a pure code, Scilab code inside XCOS using it's called scifunc block. Maybe I can look it up on if you want in the help. Or you can use what we call the from workspace block that lets you import values, so data, from your Scilab environment to the beginning of your to XCOS at the beginning of your simulation. So you're gonna have that from workspace block is gonna just have outputs it's gonna, at the start of the simulation, it's gonna fetch the values from the Scilab environment and use them as an output for this block inside Xcos. So those, depending on what you want to do you want to use data or write code inside Xcos? The two ways are possible.
Yeah, and basically that is also the question of Eric. Yeah, you can write that as a block in Xcos to write Scilab function, Scilab script. Well, I suggest for those questions, for example, Michael here is a bit specific on how you want to well interface Scilab with your embedded systems. I suggest that we take contact afterwards directly in order to investigate it, because there's not so much available material at the moment on the serial communication toolbox where you can directly interface your hardware through the RS-232 communication protocol, or also, well, yeah, I mean, let us directly take contact afterwards. I will let you my contact, and I will send you an email, and we can go a bit more in detail about that. And yeah, also, as you mentioned, Michael, the Arduino topic may cover some of this. It's basically exchanging data through the serial port. So if it's yeah, if it's not such big real-time constraints that you have, you might want to try it with Arduino. It's a really low-cost, easy to program and prototype platform. Here is a link from Paul on the From Workspace blog. Anybody's asking about some information about hardware in the loop with Scilab. So basically, there are different strategies at the moment to do this kind of thing with Scilab. Basically, well, 3 different methods. The first one would be with some hardware interface such as the Visa toolbox, where you can acquire your data, your signal directly within Scilab on a desktop PC or on a real-time PC, but running a Scilab and well, making some data feed, for example, trying to model your signal and control back the instrument from it. This would be the first method. So the second one would be on code generation, but on the subject, it's a bit generation for different platforms. From Scilab and from Xcos. As I mentioned earlier, there's STMicroelectronics, which is working on interfacing the hardware of the STM32 from Xcos directly. But it is a large subject. So, and the third one was actually a bit different from the approach of MATLAB. Is, well, basically you get the ability to compile lab on as I mentioned, on the ARM platforms on Linux, and what you can do is, well, there's, for example, but also once again low cost and entry-level approach with a Raspberry Pi. You can have your Scilab running on the Raspberry Pi, and well, you can basically run the same algorithm in this, well, embedded platform as the ones that are running on your desktop environment. So this would be the third option of Scilab directly running on your target hardware. So, but once again, it's a bit of a tough subject. We can just, yeah. So. Do you have any further question here? I think Bignesh had a question, and yeah, if Paul answered it, about the
yeah, it's good that WebEco is letting us go further. So it's, as I said, it's great for us to have a direct interface with our community, our users, because they're the ones that we need to understand the needs of. So thank you for taking the time for listening. And we're here, we're there, so we have time. So if you want to ask more questions or extend on a certain topic, don't hesitate. We're there for that.
Yeah, I'm gonna let you my email, and also I will send you an email so we can just get in touch and speak about it directly. Also about some further webinars, well, we're considering some further subjects. Here we see that's a subject about well, system modeling. Hardware in the loop is one of this subject, but on system modeling and so,
Laura, there's going to be we're going to upload the webinar on YouTube, so we will send a follow-up email with the link, so you can watch it over if you missed the beginning.
Yeah, so thank you everyone for participating. Thank you, Umberto and Humberto. Yes, just mentioned. Yeah, for further webinar also stay tuned. And thank you for joining us this afternoon. Well, it's afternoon in France. Thank you for joining us. It's been a pleasure, and well, we hope to see you next time.
Stay tuned.
Bye bye.